When Tyson fought Paul late last year, the sheer demand stressed the internet's infrastructure. At its peak, 65 million individual streams were pulling live videos simultaneously. To put that in perspective, the largest physical stadium in the world holds about 150,000 people. Netflix had to deliver a flawless high-definition broadcast to an audience more than 400 times that size, all at the exact same second. Traditional streaming bypasses this problem with video on demand. Complete movies are processed days in advance and pre-positioned on servers near your house. If millions of people watch a popular show on a Friday night, they rarely click play at the exact same millisecond. Live video operates under a punishing time constraint. Every single frame of the broadcast must be recorded, encoded, packaged, and shipped across the globe in strict 2-second increments. There is zero margin for error. If a server takes even an extra half second to write one of those video chunks to a database, that delay ripples outward through the entire network, causing the broadcast to freeze on millions of screens worldwide. Standard server architecture simply cannot survive that kind of synchronized real-time pressure. To handle the load, Netflix had to build an entirely new checkpoint sitting between the cameras and the viewers, a system they called the live origin. The process begins right at the edge of the ring. Professional cameras capture the raw footage, chopping the live action into those constant 2-second segments. Because of the chaotic nature of live hardware and strict publishing deadlines, these incoming feeds are frequently flawed. Segments arrive with dropped frames, missing audio samples, or completely mangled timestamps. To counter this, Netflix runs two completely separate encoding pipelines at the same time. The raw feed is sent to two different geographic cloud regions, using different hardware encoders to process the exact same video. The live origin sits directly in the middle. As the segments arrive, a packager inspects the media and tags any defects in the metadata. The origin reads these tags instantly, checks both incoming pipelines, and grabs the first clean, defect-free segment it sees. Because the pipelines use completely different cloud infrastructure, a corrupted segment on one path is almost always clean on the other. A local encoding error at the stadium is corrected before a single viewer ever notices. Once the origin selects a clean segment, it has to save it to a database so the global network can retrieve it. This write operation must be completed in under 500 milliseconds. This creates a massive bottleneck. The moment that segment is ready, thousands of Netflix's top-tier edge servers all try to download it at the exact same time. This massive spike in simultaneous requests is known as an origin storm. If a single database tries to handle both incoming video and outgoing requests, the volume of reads completely overwhelms the system. The incoming video segments literally cannot be written to the drive fast enough, effectively killing the livestream. To solve this, the engineers split the storage architecture entirely. They routed the incoming video into Apache Cassandra, a highly resilient database system designed to guarantee that write operations succeed even if an entire availability zone goes offline. Then, they placed EV Cache, Netflix's custom distributed caching system, directly in front of the storage layer. This acts as a massive shield, absorbing up to 200 gigabytes per second of read requests entirely from cache, leaving the Cassandra database completely free to ingest new video. By physically separating the read and write paths, the system guarantees that no matter how many millions of people tune in, the sheer volume of viewers can never block the broadcast from actually being recorded. After leaving the live origin, the video travels outward to Open Connect. This is Netflix's Custom Content Delivery Network, CDN, which places physical servers as close to your internet service provider as possible. There is a timing problem at the very edge of the live broadcast. Because devices know another segment is always coming, they often send requests for video slightly before the origin has actually finished publishing it. Normally, a server would return a not found error, forcing the device to constantly ping the network until the file appears. Instead, the live origin uses a held request optimization. It keeps the connection open for those few extra milliseconds, instantly dropping the segment the moment it publishes. Netflix paired this with a strictly predictable publishing template. Because every single video segment is exactly 2 seconds long, the servers can calculate precisely when any specific segment in the future should exist.
This math allows the edge servers to do their own triage. If a client app requests a segment that shouldn't exist yet, the edge server instantly rejects it locally, rather than passing that useless request all the way up the chain to the origin database. These localized optimizations form a massive filtration system. By holding early requests and mathematically rejecting invalid ones, the edge servers prevent billions of wasted network signals from ever reaching the core infrastructure. Even with every optimization running perfectly, an event peaking at 65 million concurrent streams pushes internet hardware to its absolute physical limits. To survive these extreme surges, Netflix relies on strict publishing isolation. The actual server hardware dedicated to ingesting the video feed is kept physically separated from the hardware handling the outbound traffic to the viewing audience. When resources run low, the origin enforces a strict hierarchy called priority rate limiting. At the top of the pyramid is database writes, the actual recording of the event. In the middle is the live edge, representing the current moment of the broadcast. At the very bottom are DVR reads, viewers trying to pause or rewind. If the system is under pressure, it avoids a crash by actively dropping this lowest priority traffic, ensuring the broadcast survives for everyone else. To prevent those disconnected users from immediately refreshing and attacking the server again, the origin instructs the CDN to cache a 503 error code for exactly 0.5 seconds, effectively muting the retry flood before it starts. True engineering at this magnitude requires building a system that mathematically understands its breaking points, knowing exactly what to sacrifice so the core broadcast survives.